Welcome to the satellite communication course. We'll continue with the Spade system. Now we say that Spade system is used if there is a low traffic, and that is useful for the improving the capacity of a SCPC Fdma system. Now here we start with the Spade system. We say that it is useful for the low traffic terrestrial interface EIF. These are the multiple channels. Channel unit 2, channel unit N. And this one is about a RF transmit receive, and that will be given to the host station. Okay, this is about your host station. Now it's about a transmitting setup for the earth station now, and then we have a demand assignment signaling and switching unit. Switching and signaling processor. Switching and signaling processor, that is SSP, CSC, synchronizer, CSC, modem, and this one is nothing but a belongs to the part of a demand assignment. Signaling and switching unit. Okay, now this is about a demand assignment signaling and switching unit. This is about a complete Spade system. Now then, how these channel units are there? How they are communicating? Okay, like so this one is a Spade system, and then for a channel unit comprises of a PCM codec, channel synchronizer, then PSK, modem, then speech detector, then a frequency synthesizer. And that is about the combined block of this channel system. For this input from SSP. Then this one we can say that to oblique from IF unit. Okay. Then this is nothing but what channel unit both the way here. Then output goes to the speech detector and then a channel synchronizer. And here input to or from TIF. Okay, from TIF. Now this one. This is about a from a TIF to the channel and then from the channel to the IF subsystem. Okay, this is about a IF. Here to channel to the IF subsystem. This one is about a channel. Okay. Then that channel consists of what? A PCM codec and all. So this one is about a terrestrial system, or you can say that it's about a Spade system, and they contains a terrestrial interface unit. They have the terrestrial interface unit, then a number of channel units, then IF subsystem, and along with that, a demand assignment signaling switching unit. Okay, this is about a demand assignment signaling switching, and then a RF system, and that particular network, if you consider, it has a control station, and that will track the status of the carrier, and then it allocates a pair of frequency to the user station on the demand. Okay. Now generally that TIF interface we say it is nothing but TIF interface to the telephone exchanges or where various subscribers are connected to this particular model, and our input or a calls are routed to the subscriber there. That is about the interface. Okay, that is from the users or to the users likewise, or through this telephone interchange or telephone exchange. And then this channel unit, if you consider, that channel unit consists of a PCM codec, then it has a channel synchronizer, then a speech detector. Okay, we have a speech detector, then a frequency synthesizer. Okay, and then a PSK modem, and that output is given to the IF system, IF subsystem. Then this IF subsystem that comprises of what? A multiplexer or a demultiplexer, up converter or a down converter, and then this DAAS, demand assignment signaling switching system, that is DASS. Okay, DASS, and that is consists of what? A switching and signaling processor, that is SSP we say, then a controlling signal channel, that is synchronizer, CSC synchronizer controlling control signaling channel, and then we have a control signaling modem, that is a CSU modem. And if you can see that a CSC modem, that CSC modem uses the BPSK to modulate the 128 kb per second CSC data. And then we have that RF transmit or a RF receive unit. The transmit unit comprises of a high power amplifier at the transmit side and the low noise amplifier on the receive side. If it is a, if you consider that the analog voice signal is there or a digital signal is there, so analog voice is coded to the PCM data using a PCM coder on the transmit side and decoded to the analog voice using the PCM decoder. Okay, that is about the PCM coder. And a speech detector detect the speech activity on the transmit side. Okay, that is about whatever the speech activity is there, that would be detect on the transmit side, and then controls the synchronizer. The synchronizer here, whichever the control comes from the speech detector there, then a synchronizer take this particular control or active whatever the active speech syllabi with a preamble on the transmit side and decode this preamble to provide the frame reference on the receive side. Then it also encode the data differentially on the transmit side and decodes it on the receive side. So PSK modem modulates, we generally say that modulate the digital data with a QPSK modulation on the transmit side if it is a digital data. So just like we can say that FM for the analog side, likewise. So if it is a digital data, then a QPSK modulation is to be used on the transmission side and the QPSK demodulate if it is in the receive side. Then the frequency generate. Here PSK modem modulator or demodulator text. And then we can say that the frequency synthesizer, it generates a carrier frequency for the modulation from the switching side signaling processor. Okay, so likewise we have the here we can consider that we have the it's separate channel for the IF system. Okay, so that's why here in the case of a frequency synthesizer, it generates a carrier frequency for the modulation from switching and a signaling processor. Okay, so because that particular information is given from this particular processor, and according to that, a frequency synthesizer, because it's from SSP. Okay, the SSP we have mentioned. Okay, that is about the switching and a signaling processor. So that is about a Spade system in which we can say that here the carriers are not fixed. So carriers are depending upon that according to the whatever the input we have. That is about we can say that that information of the frequency is allocated by switching the signal processor to the frequency synthesizer at the beginning of the call there. So that is about your Spade system. Okay, that will work. So now if you see that a Spade frequency plan where this particular Spade system is used. So initially that Spade system was used in Intelsat, and in that Intelsat standard satellite Spade system, SCPC system, they have the carrier separation of a 45 kilohertz. That is about a separation of a carrier. That is used in what? A Intelsat. Means what we can say that means every users on the earth station transmit or a receive that particular such carrier. Okay. So generally typically transponder has a 36 megahertz of a band, that is a bandwidth for this particular transponder, and they can accommodate of we can say that a 800 carriers, that 800 carriers with 45K separation. Okay, Means what we can say that we have the Spade frequency plan, and if you see that, so we have the channels likewise one, two, three. We can say that right? We have the n. Means we can say that here that each band is of what we can say 45 kilohertz. That is about the separation bandwidth. Or we can say that a 45 kilohertz of a carrier spacing. This total band, you can say that likewise one, two, three. Sorry, that is about a n now. So this is about a 18 megahertz here, 18 megahertz here, likewise. That is about a total carrier is supposed to be I just like right here. So that is nothing but a 400 in each side. Say that from this one, two. So there may be a 400 here. So 399. Okay, likewise. So means total is about the 800 carrier. So that is about in a 36 megahertz of a bandwidth of a transponder, it accommodates 800 carrier with a separation of a 45 carrier. If we consider that all the 800 carriers, it is supposed to be transmitting the all 800 carriers. So then what happened? So power transmitted from all the carrier that may exceed the capacity of the transponder. Even if that sufficient bandwidth is available, the system is not able to carry all channels because that available power rather than the available bandwidth that will limit the a total number of carriers that will be transmitted. We say 800 carriers, but if all the 800 carriers means there will be limitations for the power. Power limitation at what? A transponder. Okay, so that's why the all channels or all the carriers cannot be transmitted there. So then that's why in this particular system, if you see that a voice activation is used, and that voice activation system that will increase the channel capacity of a SCPC system. If there is a low activity, suppose we consider that, so means instead of that 100% transmission of the carrier, we can say that for the low activity factor, so actually transmitted carrier that will be less than the 50% of the total time. Means we can say that at that any instant, the total number of transmitted carrier will not be 800. The total number of carrier transmitted, it will be a 400 or less than the 400. So means in this pair system, the carrier frequency is not allocated. Okay, carrier frequency is not allocated to a station permanently, but it will be allocated on demand. That will be allocated on the demand. So why? Why? Because the call activity generally it is a low. Means what you can say that percentage of time that call is active that will be low. So that's why that carrier allocated for the east earth station is not permanent. and it is depending upon that demand according to the demand. So that will be allocated. So that's why that network can support more earth station than the maximum number of available channels, because no carrier is permanently assigned to any station. If a call is originated by any subscriber from this TIF model, then what happens? That TIF directs the signaling information to the switching signaling processor, that is SSP. Then SSP send a request using the CSC modem for a carrier allocation in the CSC channel to the control station. When the frequency pair available in that particular pool, then that frequency pair is allocated, and then the assignment information is received through the CSC, and then it will be decoded by the SSP, and then that switches the incoming call to a channel, and also control the whatever the frequency required to generate the frequency carrier. So that's why for this channel, so frequency synthesizer is used for generating the carrier. Frequency synthesizer is used to generating the carrier for the given channel there. So that is about a role for this channel there. And the PCM coder, here we have a PCM coder that will convert that analog voice to the PCM data at a particular rate. And if any silent intervals is there in a speech detector, then the role of that speech detector that will remove the silent interval in that particular speech to conserve the transmitted power. So means a total power requirement for the speed system that will be minimized there. So that's why here we have the channel synchronizer is there, and that channel synchronizer attaches some header information to the active digital speech and send it to the QPSK modem for the modulation. Then which modulate the carrier provided by the synthesizer, and then that output of this will goes to the IF there. Then IF subsystem multiplies the output of all the channels. Okay, it will multiply all the all the channels, and then I then up converted here. Whichever the IF spectrum is there, that will be up converted to the uplink frequency, and then RF unit amplifies the signal with the respective output power. So that is about at a transmission, and at the receiver, the low noise amplifier is there, and we have the IF subsystem that will demodulate or down convert that. Here we have LNA system that will down convert the system signal. Then IF subsystem down convert the carrier to the IF band. Then demultiplex the carrier is demodulated by the QPSK. Here we have a QPSK there, and a PCM decoder we have convert the data to the analog voice, and then after that that will be sent to the TIF. Okay, that will send to the TIF here. So if you consider that a whole speed system, so that system cannot support a all carriers, means 800 carriers simultaneously. So means it will use only that required channels based on the particular demand there. So if we want to use that paid system, so more than that particular carrier, but it has only 800 carriers, but they can support a more than that 800 station, because it at a time it will support only a 50% of it, that is about 400 carriers. Means total allocated system we can say it is about support 800 carrier, but a digital voice channels or a voice activated carrier based on the demand, so they can allow more than that 800 stations that will be supported by the Spade system. This one is about a Spade system. So we can calculate that according to that what will be the capacity of a FDMA system. The capacity of a FDMA system is nothing but what? A number of carriers that FDMA system supports. And that number of carriers that FDMA system support, that is depends on whether the system is power limited or whether the system is what we can say it is about the bandwidth limited. Whether your system is power limited or your system is a bandwidth limited. In the case of a bandwidth limited, okay, in the bandwidth limited case, so generally we need to assume that the power handling capability of a transmitter is unlimited. Then the number of carriers of equal bandwidth that can be transmitted by is your system, that will be given by that k is equal to what? Brf by b. So that is nothing but Brf is nothing but what? A effective RF bandwidth, and that b is nothing but what? A bandwidth of each carrier. And this effective RF bandwidth, that is nothing but what? A total bandwidth minus total guard band. Okay, that is nothing but a effective bandwidth. So this effective bandwidth we have considered that when we have the no limitations of a power, unlimited power, in a unlimited power condition, or you can say that unlimited power handling capability of a transmission channel, the number of carriers of equal bandwidth that can be transmitted by a system is given by k is equal to Brf by b. And that effective bandwidth we say that it is nothing but a actual bandwidth minus the guard band between the carriers there. And that guard band is nothing but what? It is a wastage of a spectrum. But Even if we say that a guard band is a vestige of a spectrum, but we require a guard band to avoid the crosstalk between the carriers. And that is nothing but what? A spilling of energy of one modulated carrier to the another modulated carrier. And again, that guard band made the easy design of operation or easy design of a carrier separation filter in the receiver there. So that is about the role of that particular guard band. So that is used. And if you consider that in terms of a what are the advantages of FDMA system, so that FDMA system, it is nothing but a earliest system, or you can say that a simple system or a simple method of a multiple access of a satellite and a transponder, or you can say that a simple system of a transponder there that will be used with a conventional analog technology. Then in FDMA, that carriers are frequency modulated, that is either with a single voice channel, you can say that SCPC, or we can say that a MCPC. If it is a, we can say that a multiplexing. Again, we can say that carriers can also be a digital modulated, that is PCM, PSK, that is in SCPC mode, and PCM, TDM, PSK in MCPC. That is about a digital modulated carrier. And if you consider that the disadvantages of the system, so if we consider that a traffic, according to the traffic, so FDMA is not suitable, or FDMA is not suitable or adaptable for changing traffic. If there is a variation in the traffic, so it is not stable. And again, for a FDMA, many transponder, or we can say that a more transmitter or receivers are required at an earth station for multiple carrier operation. Okay, for multiple carrier operation. So that's why that system will be a costly one. Even if supposed to be a single carrier transmission is used, okay, even if we can consider that a single carrier transmission, even if it is a single carrier transmission, so multiple receivers are required to simultaneously receive the many carriers. So we can say that a FDMA system is inefficient in terms of utilization of power, because of if there is a multiple carrier, utilization of power with a multiple carrier. Even if supposed to be, if we say that if a sufficient power is there, even if there is sufficient power, then there is a limitation for the bandwidth there. Even if that sufficient power is not available, suppose, okay, then the available bandwidth cannot be utilized fully. Available bandwidth cannot utilize fully. Again, we say that a MCPC system, so number of whatever the carriers required or number of channels transmitted over a given particular carrier cannot be changed for a short notice. So because number of channels changes, so then carrier bandwidth changes with the number of channels. Again, it has some intermodulation distortion, and to avoid that intermodulation distortion in a multiple carrier, so that's why we need to use that amplifier is to be operated in the linear mode. Okay, linear mode of operation. So that's why we can say that there is a strict control of a output power, strict control of a transmit power of each carrier is required to keep the transponder operation in the linear mode. Okay, otherwise what will happen? Then input back of a transponder or that will occur, and that will result in the reduction of the available bandwidth or available output power. And again, we have the wastage of a bandwidth because of the guard band required for the separation of a channel, that will reduce the capacity. Okay, again, guard band, guard band, that will reduce the capacity. And these are about the disadvantages of the FDMA system. So we have seen that advantages and disadvantages of FDMA system, but we need to know about what are the various applications of the FDMA system. So application generally, a FDMA system is to be used in a satellite communication in earlier days. So that's why we have mentioned that in advantages itself, it is the earliest system or a simple method is there. So applications are what it was a first multiple access technique. That's why it is used in a satellite communication due to its simplicity. And in earlier days, the carriers were FM modulated with the analog signal. So that's why that FDMA system was looks like a natural choice of a system. Then it has a MCPC FDMA is used when the traffic is large with the carrier of a FDM multiplex carrier. An earlier system, that is about Intelsat, they employed or they use this FDMA for the satellite access. Then later on that instead of MCPC, then SCPC system is used in the Earth station to transmit the single channel for the low traffic communication. And then a Spade system is used to increase the traffic or to increase the number of carriers. Sorry, to increase the number of channels. And that Spade system is a demand assigned SCPC system. Or you can say that it is a Spade is nothing but what? A single channel per carrier, PCM multiple access, demand assignment equipment there. And it has the advantages that the available carrier could be used by the Earth station at many time or in a many number. And that carrier is assigned only on the demand when the call originates from the station. And that's why this allows the carrier to be shared among the many users. Okay, single carrier can be used shared by the many users. And that is about a speed system. And that is the end of a FDMA system.